This video will provide an overview of how to train MIM-Refiner models with the official codebase from GitHub. So I downloaded the repo into this file here, and then there's in the README, we have this section, train your own models, which tell you to follow the instructions from setup code, setup data, and setup models. We will jump right into the code setup in order to showcase some things here. So we first need to set up the environment. I already did this in my case because it takes some time to download Torch and all the CUDA stuff. Um, so here you can then install some specific versions of Torch if you need. And what is important is that we need some additional configuration files, such as the static config YAML. This will tell the code base where it can store things, where it can load pre-trained mask image models from, and where it can load data, for example, for ImageNet. So how do we do this? I provided here two templates for the static config, one for development and one for training on an actual production environment. Here it tells us this model path, output path, and where it can find ImageNet. These are all paths here. For example, here this is the save path that I already set up. Here's the ImageNet folder that I downloaded, which has a train and validation split with all the 1,000 classes in it. And here it's like some images. For the development machine here, I only have a subset of ImageNet downloaded. And the third path here is the models path, where you would download pre-trained mask image models. Here, for example, I downloaded data to back 2, the base model, which we can then load for training it. All right, this is the setup to set up the code. There's some additional stuff that you can set up for weights and biases logging or Slurm log, running things with Slurm, but that we don't need here for a showcase. In order to train an actual model, here we have a configuration. So I decided what kind of hyperparameters I want to use. I want to train it on a local machine, so I have this main train script here. For the configuration via Slurm, you would use main sbatch to submit jobs in a similar fashion. This hyperparameter tells you what the actual run is, so what model do you want to refine, what are the hyperparameters, what kind of dataset you want to train on. Then the dash dash devices will tell you how many GPUs and what GPUs you want to use. For example, if we would use 2 GPUs, we would here define 0, 1. This is only a development machine, so I only have one local GPU here. And for this tutorial, we will use this dash dash test run flag, which will scale down model size, training duration, and batch size, and so on, to be very quickly executed just as a showcase here. For an actual training run, you would omit this flag, but for this tutorial, we will use it here. And then you can already get started. So we have some YAMLs provided here in this YAMLs folder. We first need to train the contrastive heads on top of the mask image model, which we call here always stage 2. For example, if you use here a large 16 model, I will copy it as a hyperparameters file here, such that we can make some changes or have a look at it without messing with the Git repo. So we train here for a short duration while the encoder is frozen. This serves as a purpose to initialize these contrastive heads here to then, when we actually train the encoder, that we get a good signal from the get-go and we don't destroy any valuable features in the pre-trained model. And here it is defined what kind of pre-trained model we want to use. For this tutorial here, I will train a smaller model here because this would be quite expensive to train. So this would define what kind of model you want to use, but here for illustration purposes, we just train a random model because it only matters that we illustrate the code base here. And then we can already start this run. So this run will, with this given hyperparameters, it will first preprocess the YAML here. So it will expand all these things here to configure them properly, that this is the class token at the last layer, this is the class token at the penultimate layer, this is the class token at the third to last layer, and then it will train it with this contrastive trainer. All these kinds are actual files in the codebase. So the codebase can be a bit overwhelming at first, but I think it's easier when you have when you actually search for these models or for these names here. So for example, the contrastive trainer here is a trainer. We have this contrastive trainer in this here, and there's a forward pass here. So we just put everything onto GPU. We merge some things for the to merge all the global views and the local views to have a more efficient forward pass. Then we iterate over all the heads, get the loss weights. If you want to actually schedule it, by default it's just a normal sum, so everything is weighted with a constant factor. Then we have the model forward passes, and we then iterate over the head and calculate some metrics, and then at some point also the loss. So here's the loss per head, where we then have the head losses, which we update or which we sum over, and then afterwards we return these losses. And this is then the thing that will be back propagated, and then the model will be updated accordingly. All these things in the YAML file where there's a kind property corresponds to one file in the YAML. For example, there's also the contrastive model, which is under models, composite contrastive model, which tells you how the forward pass actually works. So here we have we get the global and local views as input. We have here these are the local and global crops, and the teacher is only the global crops here. We do a forward pass for this. Then we concatenate outputs for efficiency reasons. If there's an EMA teacher, which we don't use typically, you can also do this. Then we propagate forward through all the heads, and we return these outputs, which are then used by the contrastive trainer here to create the loss. So here are then the head outputs. And yeah, so let's see what the actual training run looked like. So I ran this YAML before here, and we see that here there's a local development GPU here. You will get some versions, what kind of CUDA version you have, torch version, some system information here, and so on. So then we get to the actual YAML here that is resolved. So as I mentioned here, we have this stage 2 processor, which will expand the YAML and resolve things like the CLS 2022 to an actual pooling. So this will be in the YAML file. We have this, for example, here the last layer, which has some here for the development run. Here I have a small queue size, a small hidden dimension, a small output dimension to make everything run on this local development machine. Then we have this optimizer with a schedule, a weight decay, and we also have here the forward pass or the model which defines the forward pass. So when we look at the NNCLR head, we have a projector, so we have the queue, we have where's the projector? There's the projector and the predictor, which are typical components in these contrastive learning setups. And then for a forward pass, we simply get the X from the encoder, and we propagate or we pool, so we extract the class token only from this X, and then we propagate it forward through the predictor and the projector here. And yeah, then we return all these things before the nearest neighbor swap, after the nearest neighbor swap, and also after the predictor, and some metrics with like an accuracy, how well the nearest neighbor swap here did, which is useful for logging, and we'll see afterwards. And yeah, whenever there's this postfix here after the CLS, for example, CLS 22 means at the 22nd block here, this head is attached. So this head here would be attached at the last layer, and this head here is attached at the penultimate layer. Here we need some kind of other pooling, so we have this VT block extractor that pools basically the 22nd block here, and then passes it to the contrastive head. And yeah, that's how you start these runs here. It can be quite long, these YAMLs, if they're resolved. That's why they are relatively compressed here with these interpolation things here, where we can reuse stuff and not write everything out. But in the actual log, you would then see all the outputs here, and yeah, also the properties for the losses. And we get some more logging metrics here, where we load data from, what kind of evaluation data set we use. Whenever we train models, we use like a small KNN monitor, which trains on 10% of the ImageNet dataset and then evaluates on the test set. So this gives you a very good intuition of how good your model currently is and if it actually learned something. If this k nearest neighbor accuracy goes down, you probably have something wrong with your model or there's some bug in your model setup. And yeah, there's a lot of log messages, how you set up optimizers, how you create the models and stuff like this. And then we get to the actual parameter counts here. So this is a very much scaled down version of the model here, just for development purposes. And then we actually start the training. So when you start training, you get this progress bar here that will count upwards. And after each epoch, you will get some metrics. So you get all the losses for all the heads here. In addition, you get things for the nearest neighbor swap. So the nearest neighbor accuracy, for example, is when you swap a sample with its nearest neighbor, how often are they of the same class? So if this is high, then you probably have a good clustering in your queue because if you swap it with the correct class, you have similar abstract concepts aligned together in this on this hypersphere representation of the queue. And this will of course also all be logged to weights and biases. After each epoch, we also save all the current model state and optimizer states to enable quick resuming or if a run crashes, and also for then initializing the next stage where we actually train the encoder then. And after each epoch, we also get the KNN accuracies. So this is the monitor that takes 10% of the ImageNet dataset, trains on that KNN classifier, then evaluates on the test dataset. Here we get 0% here because this is a very small dataset, so it doesn't even have all the classes in it, but it's just for illustration purposes. And same thing here for the second epoch. It will create all the same metrics, and then afterwards we have finished training, and our log is finished. If we then look into the save path, so we have here this one here is the one that we currently trained. We get all these logs, so there's the hyperparameters that we pass to the command line, the resolved ones. We also have all these logs that are showed here in a text file, and we have all the checkpoints here. And we can now load these checkpoints here to refine our mask autoencoder. So how we do this is we take the configuration file for the stage 3 here, and I use the L16 MIE. So we simply copy this into the hyperparameters file, and we see that here on the top we have a stage ID. So this defines where the model will be loaded from. So we need to change this to the one that we currently trained with. And this is very similar to the one that I used in stage 2, except that there is now this optimizer for the encoder. That means that the encoder is actually trained and not fully frozen. But since we now have very good contrastive heads, we changed some parameters here, like the top k parameter for the queue, for the nearest neighbor lookup. It will not only be swapped with the nearest neighbor, but with one of the 20 nearest neighbors. And since our contrastive heads are already very good, this is a very strong form of augmentation here. And yeah, other things follow very similar to the ones from the stage 2 configuration file. It's just that here every model has this initializer, which tells you from the previous stage here, I want to load this model here and initialize the weights of this head here with this model, and then train it from that point on and not randomly initialize it. And similar to this, we can just simply run this, which will automatically load all the checkpoints, set up training, and then train the models with the corresponding uh, losses. And when this gets started here, we see a similar pattern here. Just log some versions here, some general system information, the setup here, what kind of CLE flags you pass to it, then the resolved YAML. This can again be quite long because we use a lot of heads and each head could be configured individually. In practice, it's not configured individually, but all have the same hyperparameters. And it's now the run finished here. Yeah, afterwards, same thing. Where do you load dataset from? Initializing the trainer, initializing the model, and then some point we will come to the actual training start, which will be here. So here the training started. We don't have any issues here with setting up the training, which is nice. So it found all the checkpoints from the previous stage as we defined the correct stage ID here that we previously trained with. Then again, we train here for 2 epochs for the illustration run here. We again have all the losses, very similar to the previous stage, and all the metrics for nearest neighbor accuracy. And afterwards, we also save the models and we get some KNN accuracies here. And yeah, this repeats for a couple of epochs and then it's finished. And after training, here it's also saving all the models here. The most important here is, of course, the encoder that is stored to the disk. And if you look at this, here it's in the save path here. So we now have a stage 3 here where we have our stage ID. And in this checkpoints folder here, we have the contrastive model.encoder. So we have either the one that is actually trained, and also we track an exponential moving average of just the encoder weights during training, which is typically a bit better than the actual last model. And we would then, this is then the refined model, and we would then load this for evaluation. And for evaluation, this is very similar. For example, if you want to evaluate the KNN accuracy here, we have here, it tells us we want to evaluate this EMA model. So we can simply copy this again. We have here our name, KNN evaluation, and the stage ID is here from the stage 3 that we currently trained with. And then when we train this, it will also set up all these things. It will load the previous model and then have a simple KNN classifier trained on top of it, which will then, which is now trained on the full dataset and not only on a subset. So during training, we only train on a subset, the KNN classifier, which is typically a bit worse. But here for evaluation, we want to know the actual KNN classification performance. And you see that you iterate, this would be the training dataset uh, where features are extracted. Then you also iterate over the test set, and then we calculate the KNN classification accuracy here for a class token and patch token. And yeah, this is then the evaluated result. Similar to that, you can do all kinds of evaluation, fine-tuning evaluation, segmentation evaluation, linear probing. Everything should be provided here. And yeah, that's pretty much it. Thanks for watching, and good luck with training MIM-Refiner models.